In this video, I will explain you AC applied across a pure inductor. So we have an inductor and across we have connected AC input. And what is AC input? AC input is nothing but E is equal to E0 sin omega t. So this will be the same across this chapter. An AC input can be represented as a variation of EMF as a function of sine. Okay. So this is the input. This is the source. Now in the last chapter we have learned that whenever current passing through an inductor changes, there will be a change in magnetic field associated with it. See, let's say we have applied an EMF across this. Okay, and due to the EMF there is a current passing through this. Now whenever, see, just assume that current is increasing gradually to a maximum value. So what will happen in the magnetic field created by this inductor? See, magnetic field will gradually increases. So when magnetic field increases, then there will be a change in magnetic flux associated with this coil. And who is producing that magnetic flux? The same coil is producing the magnetic flux, and the same thing is changing with respect to time. So whenever magnetic flux linked with a coil changes, what will happen? There will be an EMF induced in that coil, and this is called as self-inductance. Here why we are calling it as self-inductance? Because the magnetic field is produced by the same coil, and due to the change in the magnetic flux associated with the same coil, an EMF is induced in the same coil. So the reason is same coil and the effect is onto the same coil. Okay, so we have learned that this EMF will be equal to minus L di by dt. So that is the EMF. This is called as back EMF. This EMF will be induced in this circuit in opposite direction. Now when this is giving an EMF in opposite direction, now we know that the applied EMF would be just equal to this value. Okay, so my point is very clear here. Now here in this case, when we are applying an EMF across an inductor due to the back EMF, we could say that the applied EMF is equal to back EMF. If at all, if that is not equal, you know what will happen? Let's say the applied EMF is 100. Now back EMF is 50. So what is the net difference? 50. And what is the resistance of an inductor? A pure inductor has got zero resistance. Now I can say that there is only a conductor that has got zero resistance. Now what will be the current passing through it? I is equal to V by R, 50 by 0, which is infinity. Which means if applied voltage and the back EMF is different, then there will be infinite current passing through this, which is not possible, right? So what will happen, you know, the whatever may be the applied EMF, if it is 50 now, then the back EMF will also be 50. Now if this is 60, back EMF is also 60. Now these are applied, we have given through AC. And what is this 50 and 60? That is the back EMF created by the same coil due to the magnetic flux linked with this coil changes. And the reason and the cause, who has produced this magnetic flux? The same coil has produced the magnetic field around it, and the same, this magnetic flux or field is linking with the same coil, and that is producing a back EMF here. That is very important here. So this is called as self-inductance, L. Okay, if you know very well about this process, then from now it will be super clear with you. So applied EMF, so this is back EMF. So applied EMF would be just opposite of this. So applied EMF is equal to L di by dt, and we know the applied EMF, right? So L di by dt is equal to the applied EMF E0 sin omega t. So di by dt is equal to E0 by L into sin omega t. Now di is equal to E0 by L into sin omega t dt. Integrate. So from di, how to get the value of I? Just integrate. So integral di is equal to I, and E0 by L is a constant, and integral of sin omega t is equal to minus cos omega t. And now it is from 0 to t, so 0 to t. 0, this is, I mean, limits are not required here, so we are anyway going to get a value right here, so we can make it indefinite integral. Indefinite means we don't have upper and lower limit. Okay, so this is I is equal to E0 by L, this is into minus cos omega t, so this is equal to minus E0 by L into cos omega t. Cos omega t is nothing but sin 90 minus omega t. See, sin 90 minus theta is equal to cos theta. Why I have converted in this way, because our input is a function of sine. Now if our output, I mean our current, if it is in the same function of sine, or if it is in the function of sine, then we can easily compare whether it is in phase or out of phase. Okay, so E0, and one more thing, this is integration, right? So sin omega t's integral is cos omega t, and divided by, we have a function here, right? Sine of omega t. So what is integral of omega t? Omega. If you know the chain rule, then you could get this value. Okay. Now E0 by L omega into cos omega t is sine 90 minus omega t, and we have a negative sign here. And one more thing, sine minus theta is equal to minus sine theta. Now this is minus sine theta, right? So this can be written as sine minus theta. So E0 by L omega into sine of, this minus will go inside, minus of 90 minus omega t. So this can be minus, multiply inside. So E0 by L omega into sine of omega t minus 90. Bring it here. I is equal to E0 by L omega into sine of omega t minus 90. See, I got a function which is also in sine. Now E0 by L omega can be written as I0, because that would be the maximum value. So I0 sine of omega t minus 90. See, compare these two. I could say that these are not in phase, because when E is omega t, this is 90 degree backward. So this is forward. When it is 180, omega t is 180. When this phasor is at 180, this would be omega t is 180 minus 90. This would be at 90 degree. I will represent the phasor diagram. Okay. Now let's say always we have to draw E, because E is the input. So this is E0 and its x projection is E0 sin omega t, and this is leading by omega t. So now this is omega t, but where is current? 90 degree backward. So I have to draw 90 degree backward from E0 phase, and this is my current, and this angle is omega t minus 90. See, going omega t, this is angle omega t, and go 90 degree backward. See, from 0 plus omega t and 90 degree backward, that is minus 90, and this is now my current I0. Its projection here would be I0 sin omega t minus 90. Now very important thing, that we know that voltage divided by, see, V0 divided by resistance is equal to I0, right? Now here I0 is equal to E0 divided by L omega. Compare these two equations. Instead of resistance we have L omega, but can I call it as resistance here? No, because resistance we know that will happen in a resistor. Okay, resistor is having resistance. Here I have told you pure inductance, which means its resistance is 0. So I can't call it as resistance, but it is having the same significance, or it is doing the same work that resistance is doing. As L omega value is increasing, the current will decrease. So this L omega is basically opposing the current. So instead of calling it as resistance, we are going to call it as reactance. Now there are different types of reactance. I am going to call it as inductive reactance because it is associated with inductor. So this L omega is inductive reactance. Very important this is. Okay. L omega is inductive reactance. See, and we got the value of maximum value of current, and we have maximum value of voltage here, that is the same. Maximum value of current is equal to E0 divided by inductive reactance, which is L omega, and this can be represented as XL. Okay, capital letter X and L. Now this value of resistance will not change unless the temperature is changing, or unless the temperature or length, shape and dimension is not changed. But here with different voltage input, the reactance values will change. How is that possible? See, our reactance is having omega in it. Self-inductance of a coil will not change unless the shape and dimensions are changed. Okay, we know the value mu 0 n square Al, right? But omega value will change. If you are using a current with 50 Hertz, then the value of this reactance would be one value. But in America, if you are using the same coil, then the value of reactance would be different, because there the current input is at 60 Hertz frequency. So when the frequency is being changed, the reactance will also change. So that is the biggest difference in between resistance and reactance. Resistance will not change with frequency of input voltage, but reactance will change. Okay. So in the coming video, we will see the same things for capacitive circuit. So this one phasor diagram is very important. And one more thing I forgot to give you, that the graph. How would the graph be? See, we have voltage would always start from 0, go to maxima 0, maxima and 0. But current, in this case, current is lagging by 90 degree. Now see, this is voltage, right? When omega t is 0, the whole function will be 0. But here, see, I0, theta and EMF. At theta is equal to 0, EMF would be 0. But what will be I0? This will be 0, sine minus 90, sine of minus 90, sine 90 is 1, sine of minus 90 is minus sine 90, which is minus 1. So this would be minus I0. Now at 180, this is sine 180, sine 180 is 0, so angle 180, EMF would be 0, but this is 180 minus 90. What is 180 minus 90? 90 itself. Sorry, before that we have to see 90. So here E0 sin 90, E0 sin 90 is E0 itself, sin 90 is 1, and this would be 90 minus 90, 90 minus 90 is 0, sin 0 is 1, so this would be, sorry, sin 0 is 0, this would be I0 into 0, 0. Now at 180, this would be sin 180, sin 180 is 0, E0 would be 0. So this would be 180 minus 90, 90, sin 90 is 1. So I0 into 1, I0. Now see, at 0 angle, this is 0, this is 90, 180, 270 and 360. Now at 0 angle, current is minus I0. Now at 90, current is 0. Then at 180, current is I0, positive here. And this would be the graph. See, I could say that voltage is leading current, or current lags here. See, when it is omega t, this is 90 degree backward, omega t minus 90. So how can I say this? Voltage is leading current by an angle of 90. With phasor diagram, it can be easily told. Voltage is forward, moving forward, and that is leading current by an angle of 90 degree. So in inductor, voltage leads current by 90 degree, or current lags voltage by 90 degree. Okay, thank you.